Hey guys, Chili here. We're going to look at the solution to the Intermediate 25 homework. It was a pretty involved challenge that I gave you, and so it's going to be a lot of detail in the solution. It's probably going to be a long video. It's almost going to be more like a tutorial than just a quick solution video, but you'll see. So get comfy and get ready to get your mind blown or whatever. I don't care. So first thing you want to do when you're going to do this homework is you're going to want to clone the repository with the solution code. Or not the solution code, but the starting code. I'm not going to give you the solution right away. You have to work for that. So we'll put that in there. We're going to give it a name. We'll call it Boxy Sol. Clone that. And there you go. So we got it all cloned. Let's make sure we've got it open. All right, so it opened it automatically for us, which is nice. So then we go home and we open up the solution. And there you go. Now you're going to look in here. First thing you're not going to notice, because you probably don't want to look at this, but there's only one configuration, x86. I removed the x64. I'll let you know why in a little bit. But if we try to build this, we can't, because we don't have box2d. I did not include it in this solution because that's not a good way to distribute it. So what you're going to want to do is you're going to want to get that dependency on your system that you can build against. And the way you do that is with VC package. So what you're going to want to do is you're going to want to navigate to the folder where you install VC package. And I'm not going to put that step in this video because A, I already have it installed and I don't want to remove it and mess up my setup, and B, it takes a long time. So I already have a video where I go through the whole process of installing VC package. You can look for that video using the convenient search feature, or you can, there's lots of other guides for installing VC package, including the official guide. So anyways, when you install it, you're going to have a folder, something like packages, and then you're going to have a VC package in here. And what you want to do then is you go shift, right click, and shift right click somewhere. Maybe here? No, maybe here. God damn it. Here we go. Open command window here. That's what I want. Got a command window. Then we can run the vcpkg command from here. We get a list of commands that we can use. One very important one is search. vcpkg search gives you a whole list of all the packages you can install. There's a lot of them. It can be pretty annoying to look through that. So you go vcpkg search box, and there you go. Box2d, our good old friend Box2d. And this is what we want to install. So what's the command for that? Well, we go vcpkg. And what do we have? We have install package. Seems pretty simple. So we can install box2d as the name of the package. So vcpkg install box2d. And there you go. It is going to download the source code for that and build it using your current compiler. And that is nice because that means that it's the thing that's going to get built, the binary, is definitely going to be compatible with the compiler that you're using. Whereas if you download pre-made binaries, you're not guaranteed that. So we've got it installed. Now if you look here, one interesting thing is it says installing package box2d x86 Windows. So if I go vcpkg list, it'll list all my installed packages, and you can see here for box2d, I've only got x86 Windows. If you want x64, you've got to specify it. So you would go vcpkg install box2d x64-Windows. And if you do this, now you can install both versions, but I anticipated that some of you probably wouldn't realize that, and that is why I forced the project here to only have an x86 configuration, just so that you guys don't get messed up, because I'm such a nice guy. So now we've got these packages. They're installed on our system. One extra step that you may or may not have to take, vcpkg. I don't know if you have to do this after every install. I don't think so. But what you want to do is you want to go vc package integrate install, and that makes install packages available user-wide. So what this will do is that means that any project that you have, it'll automatically be aware of and will be able to link to any packages that you installed with VC package. So I will go VC PKG, integrate, install, and there you go. Now linking will be handled automatically. No worries. It's the beautifulest thing ever. And now if we go here and we go build solution, you can see we get a little bit of a different picture. It builds, it succeeds, and we're ready to go. We're off to the races. So if we run this, we can get the little test. And if you look down here, a lot of you might have not have noticed this, but if you run it with the debugger attached and you look at the output, you can see here I'm outputting all of the collision events to the debugger console. So right now you can see that in the code that I gave you to start, you've already got some collision detection being handled in here, and that's a good thing. So you're going to want to look at that when you start to deal with collision detection on your own. So that's basically the first task I gave you, was just to get the thing to build and run. Now the next task that you were tasked with was to, try to figure out how the whole code base is set up. And that is probably going to be one of the hardest parts of this little challenge here. Now, there is a little bit of saving grace in that you're working with the framework. You have an idea of the entry point of how the flow of a frame works, right? You're going to initialize your stuff in game constructor, and you're going to be using go is the thing that's going to be called, and that's going to be calling update model and compose frame. So you can look here to get an idea of what the top level looks like, and you can look in game dot where is it? We can just do this in game.h, and you can see what some of the top level data constructs are going to be here. So this is a good starting place to look at. And what you're going to notice is you're going to notice B2 world, and you're going to notice, you got a pipeline here, frame timer, and RNG. These guys are probably pretty familiar to you. Boundaries is not familiar, and box is not familiar. So you're probably going to want to look at those guys and see how they do. Now, the main thing here, you're doing a simulation of boxes, so you might want to look at what box is like. So if you go to box.h, you look in here, you're going to get an overview of all the things that you can do with a box. Just looking at the interface here, what can you do with a box? And you can, let's see here, you can draw a box. Obviously, you can construct a box, and it takes a bunch of different things. It takes a position, takes a size, angle, stuff that you might expect it to take, and you can get the size of the box, you can get the velocity, the position, the angle, all that stuff. So it's a fairly straightforward interface. One thing that's a little confusing is this color trait thing. I'll get into that in a second. Another thing that's a little confusing, especially if you haven't looked at the 3D fundamental stuff, is the draw method, because it's taking something called a pipeline, and it's doing stuff like bind to translation, bind to rotation, it's using matrices. So this might be a little confusing, but the first takeaway for this, the first thing you have to understand for how you should approach this situation is that in your simulation here, in the tasks that you were given, in nowhere does your tasks involve you having to change the rendering pipeline of the code base here. You're tasked to do things that change the actual physical simulation, splitting boxes, or causing boxes maybe to change their color, and that doesn't actually require you to fiddle with the rendering pipeline in any way. So the important thing here, the important thing that you were required to do, is to realize that this is not super important, and to put it out of your mind. And that's a pretty important skill for a programmer to be able to do when they have to jump into code bases that they don't understand to find your way around. You have to first identify the parts that you can kind of ignore so that you can focus on the more important parts. Because the idea of anything in programming is to break a big problem down into smaller problems and then tackle them individually. And the less problems that you have to tackle, the easier it's going to be to get started. So, that being said, let me just do a quick overview of how this works, because, I don't know, it might be mildly interesting for some of you. So the pipeline is the pipeline in 3D Fundamentals, and the way it works is you feed it triangles, and it will draw those triangles. Now, the pipeline is configurable with an effect. It's templated, and the effect that we have is a solid effect. And all the solid effect does is it takes in vertices, and it doesn't really do much to them except it applies a transformation. So it rotates them and scales them and translates them on the screen. The geometry shader doesn't do anything. You forget about it. It's just a pass-through. And in the pixel shader, what it does is it draws the triangles with a certain color. So you bind a color to the pixel shader, and it will use that color to draw the triangles. So this one only draws solid triangles. Now, one little thing that's different from the 3D Fundamentals code is, let me see here. So this vertex shader, it takes an input of vec2. So it's actually inputting two-dimensional vertices, and then it transforms them to three-dimensional vertices for the rest of the pipeline, because that's how the pipeline is set up. So for this shader effect, we actually pass it two-dimensional triangles, and it will transform them into the third dimension for use in the rest of the pipeline. So in box, we have a static index triangle list, and all index triangle list is a list of vertices and then a list of indices used to draw the triangles. So for those of you who aren't familiar with 3D Fundamentals, let me just give you a quick overview. Index triangle list is going to have a list of vertices, a vector, and we'll number them 0, 1, 2, and 3. Now let's say with these vertices we want to draw a quad, just a rectangle basically. So what we're going to do is we need to specify what vertices we need to use to draw two triangles, to draw this quad. And the way we do that is, well, the two triangles that we want are going to be this one here and this one here. It's not the only way you can do that, but it's the way I'm going to do it. So that means we want to draw triangle, vertex 0, 1, 2, and then we want to draw another triangle with vertices, I don't know, 1, 3, 2, like this. And that is all that we're doing with this index triangle list. So when I initialize it, I'm initializing it with the vertices. And you see here, this is a rectangle. If you actually, plot this out, it's going to be a rectangle. And here we got 0, 1, 2, and then 1, 2, 3. So I think I labeled my vertices a little differently. I put them in a different order here, but it doesn't matter. You get the idea, and that's all that matters. So this is called once when the first box is created. It calls it init, and init checks to see if the model has been initialized. If it hasn't been initialized, it just initializes with the vertices and indices. And there you go. You've got your model all set up. And and then when it's time to draw it, you pass in a pipeline. And for the pipeline, we set up the translation vector. That's going to be used to translate all of the vertices. We set up the rotation, which is kind of misnamed because it's rotation and scaling in there. So the scaling takes the size of the box, because I made it so that different boxes can have different sizes, and this will scale by the size of the box, and this will rotate by the current rotation of the box, and that is how we're going to draw those triangles on the screen. And we bind the color to get the color of the current box, and then we draw the model of the box. We pass the vertices, the triangles, index triangle list into the pipeline, and it draws them based on these settings. So there you go. That is how the drawing works. It's not super important to finish this homework, but it might be interesting. Now, one interesting thing here is the color trait. So the boxes here, they can have different colors. And the way I decided to do that was I decided to give the box object a color trait. It's a pointer, and it's a pointer to a color trait object, and this object is going to be polymorphic. So you can see here I've got a bunch of pure virtual functions, and those are going to be overridden in a bunch of, I don't know, child functions, derived functions. So if I go to color trait, it's got to be in here somewhere, right? I mean, it's got to be in here somewhere, right? So the color traits are actually defined in box.cpp right here, and you can see they're implementing here those pure virtual functions. One is to get color, which just returns the color, and the other one is clone, which returns a copy of the current color trait. And this is going to be very useful in the future. But you might be wondering why I did this design. It's definitely more complicated than it needs to be, because instead of having this whole color trait thing, why don't we just store the color directly in box and use that? And that would actually be a better solution for the current situation. But in more complex scenarios, where you're not just getting the color, where your traits might have a whole bunch of different complex behaviors associated with them, it would be much better to use a class. And this is also going to enable me to do a little trick that I'm going to show you for the pattern matching that is really neato keen. So that's why I went with this little design choice here. It's not particularly suited for this simple example, but it will scale much better for more complex scenarios. All right, so we got the color trait, and that's what we use to get the color. We just call get color trait, and then we call get color on that, and that is what we use to get the color that we draw the box with. And so that is basically how that works. Now, the other thing that you're going to want to obviously understand is, how does this box 3D stuff work? Box 2D. Box 2D. We don't have box 3D yet. And the way you figure this out is you do a Google search. Let me just bring it up here. So you do a Google search for box 2D, you get this. You click on it, you go to documentation, and you look at the user manual, and there you go. You've got pretty much all the information you need right here. And you might say, but Chili, this is there's like tens of pages here. You want me to read? The answer is, yep, you have to read. Reading is pretty important when you want to be a programmer. Reading documentation, learning about shit. And here it's going to give you a general overview of the concepts, and probably most important thing is it's going to give you a little bit of a hello world example that you can use to get an idea of what you need here. So the first thing you create is you create the B2 world, and the world represents the entire simulation. All of the things in your simulation are called bodies, and they live in the world. So you create the world, and then you use the world to create bodies, and then you call step on the world. Where is it? It's going to be around here. Yeah. Maybe here? Yeah. You call step on the world, and that advances the simulation and does all the calculations for a given time step. So you call step repeatedly in a loop, and then you have an animated simulation. So, reading this, you will understand, oh, well, I guess I need a world, and looking at game.cpp or game.h. Now, game.cpp, you'll see here I create the B2 world. I give it a vector with a very mild gravity in the down direction, and that's the starting point. So you need a world, first of all. Next thing, you need to put some bodies in the world. You let the bodies hit the world. And how we do that is I have encapsulated the body creation bullshit in the box class. So you don't have to, when you're creating a box, you don't have to worry about anything to do with box 3D. It's all encapsulated in here. So to create a body, you create a definition for the body. You tell it the type of body. Dynamic bodies, the two things that we're worried about here is dynamic and static. Dynamic participates in simulation. Static just sits there as a obstacle for other dynamic bodies. So boxes are going to be dynamic because they're going to be flying around in space. They're going to be hitting things. So you make it a dynamic body, give it its initial position, velocity, give it an angular velocity, give it an angle, and then you create the body. Now, creating the body, and this is another hard part to understand. This is why I told you this code is not going to be easy to wrap your head around, because I'm doing a lot of things that aren't super straightforward, but that make your life easier once they're in place. So normally here, what you would do is then you would call a function on the world to create the body, and it would return to you a pointer to the body that was created. What I'm doing here is I have actually created a new type called a body pointer, and this is a unique pointer, because when you create a body, you get a pointer to that body in the world. But when you want to destroy the body, you can't just call delete on that, because it wasn't created with a new, it was created with a call to world. So to delete a body, you also have to delete it with a call to world. So what I want to do is I want a smart pointer that when my pointer goes out of scope, my pointer to the body goes out of scope, it will automatically delete that body from the world. And in order to do that, you have to use a custom deleter with unique pointer. And I don't want to have to do that every single time I create a unique pointer to a body. So what I do is I create a new type called body pointer. It inherits from unique pointer. It is set to point to B2 bodies, and it takes a std function, and that std function wraps functions that take a pointer to B2 body. And what it's going to do here is we're going to create the, when we have a static function called make in body pointer. It takes a reference to a world, and it takes a reference to a body definition, and it will create that body in the world. And this is going to return a pointer to a body, and that is going to be used to fill, because this returns a body pointer, so that's going to be used to fill a body pointer, which is just a unique pointer here. So this creates basically the unique pointer. But to create this unique pointer, you need not only the pointer to the body, the pointer that's going to be managed, but the actual, you're going to need the deleter function. And the deleter, we'll just create that as a lambda. It's going to capture world by reference, and the lambda takes a pointer to the body, and it calls destroy body on world with that pointer. So here we've encapsulated the whole idea of a smart pointer to an entity that lives within the B2 world. And that's nice. And then here's the actual constructor, which just takes the two things and fills them into the, constructs the underlying unique pointer using those things. So there you go. You've got a body pointer, and it's much nicer typing this out than typing all this bullshit out. And if we go back to box.h, we just call body pointer make. We pass it the world, we pass it the body definition, and it gives us a smart pointer to our newly made body. And that is going to get filled into here. So now we've got our body. But bodies by themselves, they don't have any shape. Look in here. Nowhere did we tell it this is a box, this is a circle, this is a triangle. There's nothing about a body that gives you its shape. So in box2D, let's just go, let's give ourselves a little drawing space here. In box2D, you've got some basic core concepts. You've got the world. That's not how you, there you go. That's how you spell that. And you've got bodies. But the bodies don't have shapes to them. They only have some basic concepts, like I think maybe density, and they store the positions and the states of your bodies. But to get the shapes of them, you need fixtures. So fixtures can be one of basically two or three things. You can add circle fixtures, and you can add polygon fixtures. Now circles, they have a radius, pretty simple. Polygons, there's a restriction on them. They have to be convex. You can't have a concave polygon like this. That's not allowed. And you might say, well, Chili, what if I wanted a body that was shaped like this? And the answer is you would actually split that into two fixtures, and you would attach both of those fixtures to the body object. So in Box 2D, a body can have any number of fixtures attached to it, and those fixtures will give it its shape. And I believe every fixture also has its own density associated with it. So by attaching fixtures to a body, you make a complete body that is going to be able to do shit in the world. So that is what we are doing here. We create a shape box, dynamic box, and that's a polygon shape. We have a easy function to set that as a simple box. We give it the half width and the half height, and then we create a fixture. We set its shape equal to the point of the box. We give it a density, we give it friction, restitution, which is bounciness, and then we create the fixture on the body. So here we're attaching a new fixture to our body, and that is going to be associated with the body. And there you go. Now we have a body in the world with a fixture. It is now ready to start interacting with the rest of the B2 world. Last thing we do is we have one void pointer on that is inside of the Box 2D world body, and we can attach our own custom user data to that. So what we're going to do is we're going to attach a pointer to our entity in our system, and this will serve as a kind of link between our entity in our simulation and the body in the Box 2D world. There's two links. There's one link is we have in our box, we have a pointer to the body. And the other link is in the Box 2D world, we have a pointer that goes from the body to our box class, our box object. So these two pointers will serve as a bidirectional link between our entity that we define in our class and the entity that's living in the Box 2D world. And this is an important concept because these two things are happening in parallel, but you want to keep them in nice synchronization. So you need to have those links established. So this is a void pointer. So that means we're going to have to be doing some casting bullshit when we want to go from the user data back to here. But we'll get to that in a second. So that's the basic idea of how you get your Box 2D stuff working and working with your own entity class. Now, when you want to do stuff, most of the stuff that's going to be done is done in the Box 2D end when you call step. So let's look at that. We'll go to game.cpp. So here we set up, I've added an extra layer to the pipeline. This is a little detour, but I've added extra layer to the pipeline so we can set a position and a zoom for the camera, and that will allow us to zoom out and in, rescale our scene, and also pan in the scene if we wanted to. But we don't want to pan, trust me, because I haven't implemented clipping here. So if you try to pan, something goes off the end of the screen, you're going to crash. So don't do that. The setting position was a mistake, but the zoom definitely important. Here we are creating a bunch of boxes in the world. So I just called generate n. Maybe I'll go over this in a little more detail. The listener, that's for another day, which is to say for a little bit later in this video. So here we get a delta time for frames, and then we call world.step with the delta time and with some magic numbers here. These numbers, the higher these numbers are, the more exact your simulation is going to be. It's going to split the simulation up into more finer grained steps. But it's also going to take up more CPU time. So I used the recommended 8 and 3 here. Now, it's also recommended that you step your simulation with a fixed time step every frame. And that is pretty important if you want a nice, a well-behaved simulation that runs the same every time you run it. But I'm not super worried about that. This is just a neat little graphical demo. So I just set my time step equal to the actual amount of time that has passed. And there you go. And then for your drawing, you're just going to loop over all of the boxes and call draw on each of them. For the boxes here, we can see we have a vector of unique pointers to box, and we're just drawing all those. Now the world boundary, I'm jumping all over the place here. Should I go now? Let's keep with the box here. So that is how the simulation of the box works. Most of the work is done in step, but obviously you're going to want to be able to get some information from your boxes so that you can use it in your own game logic that is outside of the Box 3D world, Box 2D. So we got some basic functions that allow us to query information about our box in the world, and it just calls Box 2D functions. Like, well, this one's not a query, but we can get the angle, we can get the position, we can get the velocity, angular velocity, and then the straight line velocity of the bodies in the world. And that's useful for us in our own code when we want to use that information to make decisions and do gamey type stuff. So there we call Box 2D and the Box 2D functions on our body, and that gets us the information out there. We can also apply external stimulus on the bodies, on the boxes, with stuff like apply linear impulse and apply angular impulse. We can also apply forces over time, but that's not part of what we're doing here. Although you could have done that in your code if you wanted to. So those parts are pretty straightforward, I hope. Again, basically, create a box, you create a body in the world, and you have some links, and then, for example, you use that pointer link to get information about the body in the world, or to mess with it a little bit, to mess with it based on the rules of your own game logic. And then when it's time to draw the body, you're going to, again, query the information from the world, the angle, the size, well, the size we store, but the angle, the position, and use that to draw the body. So that's the one main body is the box. The other one is the boundaries, and they are a little different than the box. Again, you see here we're using our body pointer, because this is also a body, but this one is a static body. So we do static body. I just give it a position anywhere, so it's centered around the center of the world. And static body does not participate in dynamic collisions or anything, in that it can't move, and if things hit it, it's not affected in any way. But it can act as a boundary for static bodies. So we specify this one as a chain, which is a different kind of B2 shape. We have 4 vertices, that's the 4 corners of the rectangle boundary, and we create a loop using those 4 vertices, and there you go. And then we just create a fixture of the chain. Friction is 0, density is 1, restitution is 1, and we create that fixture on our body, and there you go. Now we have a body. It's just going to sit in the world and act as a boundary for all of our boxes. And that's pretty much, this is incredibly simple. And that's why you don't have very much code here. But I mean, you could have done this with a dynamic body as well, or with a number of dynamic bodies. But the problem with that is they're going to take up a lot of simulation time. It's going to be annoying to try to fix them in space. And it's pointless, just extra wasted simulation. Make the things that don't move, make them static. You can't lose. So now you got your box, you got your boundaries. You're now ready to take on the first part of the challenge. And the first part of the challenge, like I mentioned, was to make boxes disappear, to make them be destroyed. Now, in order to do that, well, the idea was if 2 boxes of the same color hit each other, they should both be destroyed. Now, in order to do that, you have to know when 2 boxes collide with each other. And that's not really super clear, because that happens during the step part here. Where is it? Game.cpp. So when you call world.step, that is when 2 boxes are colliding. And what happens is the world is going to take that collision, and it is going to resolve it. And at the end of that, they're no longer going to be colliding or touching usually, because they're going to have bounced off each other. So you have to have some way of being able to detect that touching condition in the split second that it occurs. And that's not super easy to do from the outside. Luckily, Box2D gives us a nice little mechanism that we can use, and we hook into it, and it will notify us of any sort of collision type events, and it will call our custom code to handle those events. So we have a way of introducing a callback into the simulation, and it does it in a very nice object-oriented way, in that it provides a abstract class B2 contact listener with a bunch of abstract functions, pure virtual functions, and we can implement those functions. And by implementing them, and by setting up our listener as the Box2D listener, that means that those functions will be called whenever two things contact each other in Box2D. Now, you might not have known where to look for this, but if you ran this in debug, like I sort of asked you to, God damn it, please just, there we go. So if you ran this in debug, what you get is you'll notice you get this output in the debug window. And you know from previous tutorials that this output is done by a function called output debug string. So you could have searched for this in the code, found it here, and that would have been one way to find this. The other way would be to look through the Box2D documentation, and you will find it mentioning Box2D contact listener. Number of ways you could stumble upon this, but here you see that I've already implemented some nice logic for detecting contacts and acting on them. So what we're doing here is we implement this virtual function, we override it, and it takes a B2 contact. And a B2 contact gives you a bunch of information about the contact. The most important ones are, it tells you what two fixtures are participating in the contact, because remember, a body can have multiple fixtures, so a contact is between two fixtures, and from that fixture you can get the body that that fixture belongs to. And first thing you want to do is you want to check to see if those are dynamic, because we haven't set up any kind of system. We're not interested in collisions with the boundaries, only with the boxes. So first we can filter, make sure we're only looking at dynamic bodies. Once we've done that, let's get pointers to our actual box entities from our side of the system. So we take the body pointers and we get the user data from those. Those are void pointers, so we have to cast that back to a box. But luckily we know that all of our dynamic bodies are going to be boxes, so that's an easy cast to make. If you had a simulation with many different types of entities, you would have to do a more dynamic cast situation where you would cast from, or you would have to use a common base type, basically. But here we've only got boxes, so box is the common base. So we can safely cast from user data to box. And now I've got an array of box pointers here. And what I'm doing here is I'm getting the type ID of these two boxes, and then I'm printing out the name of the type, not the boxes. I'm getting actually the type ID of the color traits, because the boxes are all the same. There's only one box class. It's the color traits that are polymorphic. So I get the color trait, which is a pointer to color trait, and I get the type ID of that. And that will, when I call name on that, that will give me the name of the actual polymorphic color trait type, whether it is a yellow color trait or a red color trait. And print that out, or build that up into a message, and then print that out. So this is the basic idea of how you can use your contacts. Now what we want to do here is basically we want to compare the two color traits, and if they are the same, we want to destroy those boxes. So let me show you how we handle that. Alright, so I switched over here to my actual completed solution code. Let's see how I do this stuff. So a couple of additions here. What I'm doing, you can see here, is so I still log the collisions between all the guys. And then if the type ID 0 is equal to type ID 1, they're the same type, the traits are the same, then I add to the message kaboom, and I call box pointers 0 dot mark for death. So here I'm actually only destroying one of the two, but you could easily destroy both. But I'm not destroying it right away. I'm calling mark for death, and in box.h, mark for death sets a flag is dying equal to true. And then I've got another function that can check the is dying flag. And here I've added a flag. So I'm not deleting it right away. And this is very important. This is something that if you guys have made it this far, you will have run into. If you try to delete, remember, this callback, where is it? I'm getting all messed up here. Wrong code. Here. This callback here is being called while box2D is in the middle of solving a step of its simulation. You can't just remove a body from the system in the middle of solving the simulation. That'll mess the whole thing up. So what you do is you set a flag. You say this thing is going to die, and you let the simulation continue running. And when the simulation is done, then you remove the stuff that is dead. So what I do is I do a remove if. I remove all the dead boxes at the end of the simulation step. And the remove if is just, boxes begin, boxes end. And I use std mem function to convert is dying into something that the predicate can use. So this will convert is dying to a function that takes one parameter. And the parameter is the actual instance of the box. And that is what is going to be used in the remove if. It'll remove all of the boxes that are dying, and then erase will clean up the garbage from our container. And when the boxes are destroyed, the smart pointer will automatically destroy them from the world. So there's a little bit of beautiful, clean resource management there. So there you go. You mark the stuff that is marked for death, and then you actually destroy it. There you go. That's all there is to that. So once you understand how the contact listener works, and once you understand that you can't just destroy stuff in the middle of a simulation, the actual destruction part is quite simple. Now, in the next step of the homework, I basically gave you a choice. You can either try to do the splitting of the boxes, or you can try to do the pattern matching for the handler. And I told you the box splitting is probably going to be easier, but I'm going to show you guys the pattern matching first. This is probably the hardest actual coding part of the homework, although you could argue that just understanding the base code was the hardest part. But let me show you guys how I did the pattern matching. I'm going to do it using using type info. Yeah, I'm doing it using type info. I told you got to use an unordered map, and we're going to use type info together with unordered map to do some good shit. So pattern matching listener. So I create a new listener class here, separate from the other listener we had before. And this one is going to match patterns between type traits, color traits, I believe. Yeah. So let me see how to explain it. We go back to the basic, the nuts and bolts of the pattern matching listener. So it's going to inherit from B2 contact listener, and it is also going to implement the switch pattern that I introduced at the end of intermediate 25. But here, we're not switching on a single value. We're switching on a combination of two values on a pattern. So in order to switch on that combination of two values, I create a pair of type info. So these are going to be the type infos of the two color traits that we're going to be using as the information for the combination. So we've got a pair of pointers to type info. Now you might be wondering why I do a pair of pointers instead of just storing type info values. And the reason why is because you cannot get a type info value. When you call type ID, it returns to you a reference to a type info. And type info has its copy assignment deleted. So you cannot make a copy of that. So you cannot get a value for type info. You can only get a reference to a type info. So we could either store this using std reference wrapper, or we could store it using a pointer. And I decided just a simple pointer is easier. So I do const pointers to the type infos of the two color traits that are going to be used in the pattern. So there's one part of the puzzle. So now we've got an unordered map. The key type is a type pair. The value type is going to be the function that will handle the collision. And that function is going to take a reference to the two boxes that are participating in the collision. And then you also have the default handler here. So there is the basic data breakdown. Now, because we have this type here, type pair, that we're creating an unordered map for, hash table, we need a hashing function for type pair, and we need an equal comparison function for type pair. So what the hashing does is it gets the hash code. By the way, type info has a function called hash code. So you can get a hash code for any type info. So we get the hash code for the first type info, call it hash 0, and we mash that together with the hash code for the second type info, and that will get us our hash code for our type info pair. And for comparison, all we do is we compare. If the first is equal to the first and the second is equal to the second, then we have the same combination. So this will allow us to compare two type pairs to each other to see if they are the exact same combination. Now with those things, now we can actually create our unordered map of type pair to function. Now we just need to implement our pattern matching. So what I've done here is I've created a basic interface where I can add patterns. I can add cases to the switch, basically. And the patterns are templated on type. So what I do is I say you give it a type T and a type U, and those will be the two types that are participating in the pattern. So you're going to give it, like, for example, a yellow trait and a red trait, and that will allow you to define the behavior when a red collides with a yellow. And so what we do here is we add the handler, because you got to pass it the two types for the pattern, and then you got to pass it the function for the handler. And I made the function also as a template parameter, because if you don't put it as a template, then things get annoying. You actually have to construct a function, std function, and pass that in. Whereas if I use it as a template, I can pass in a lambda directly, and that makes the syntax on the calling end a little nicer. So we get the function, and we assign that to handlers at the pair, the combination of T and U. And I also want to assign that to U and T. But if I get them in the opposite order, I also have to pass the parameters to the function in the opposite order. So I use std bind to swap the order of the parameters into function f. So here the second parameter goes in first and the first parameter comes in second. That's one way you can swap the parameters. The other way is you could use a lambda here, and that would also enable you to swap the parameters easily enough. But I decided to be a little cute. I'm going to use bind. So here we're basically assigning this function to both permutations of this combination here, T and U and T. So they can come in either order. The other way you could handle this is you could make this comparison here. You could make the hash and the comparison such that they would be the same regardless of the order of the parameters here, regardless of which one is first here. Whether you could basically swapping of the order inside the pair would not change the result of the hash or of the of the comparison. You could make it that way, but I decided instead just to bind the function twice to different orders, because maybe in some situations you might want to have different behavior depending on the order of how they come into this function. I don't think that would be usually the case. Usually you would want it to be symmetric, but you might have situations where you'd want to have different behavior depending on how those parameters come into the handler. So here you can bind handlers to certain patterns of type traits, not type traits, color traits. Here we can just check to see if one has already been bound to a combination. Here we can clear if one was bound, and here we can set the default. So that's all pretty simple, right? Now here comes the actual magic, the switch. So switch is going to switch on boxes. Even though we're storing color traits, pairs of color trait types, we're switching on boxes. So how do we do that? Well, first we want to find the entry in the unordered map. So we have box A and box B. We get the color traits. We get the type ID of those. We get a pointer to the type ID, and then we create the pair out of those using the curly braces. So this creates the pair, and that's what we're storing in our map. And then we use find to try to find the thing in the map. If it exists, we call the function with A and B. If it doesn't exist, we call the default with A and B. And there you go. Bob is your uncle. You now have the ability to switch on boxes, and that will switch depending on the color trait that is in the box. And that will pass the box to the handler of that combination. And then here, to implement the be contact listener stuff, we have can begin contact override here. And similar to before, out of the contact, we get the body pointers. We check to see if they are both dynamic. If so, we switch on the box pointers that are maintained in those body pointers. And that will execute whatever handlers that we have attached to that combination of color traits. So that is the pattern matching listener. Now, for reasons, I don't know why, doesn't really matter, I split off color traits into their own header file. No biggie there. Same stuff, just in a different file. In box.cpp, I deleted the color traits from here. Basically all I've done. Index triangle list. And then here we have the spawn. Oh, I never described the spawn function. So I guess I better talk about that now. Spawn is a simple factory function. You pass it a size of boxes that you want. You pass it the boundaries that you want to spawn the box inside of. You pass it the world that you want to spawn the box inside of, and you pass it a random number generator, and it will generate a new box and return a unique pointer to the box. And it does that, with just uniform distributions, creates a box. It will create it with a random color trait, and it'll return that. And this is what we use to then generate. We use this function to generate boxes in game.cpp. Let me just go here quickly. You can see generate n will generate n boxes inside of the boxes container. So where is it? So yeah, we create a back inserter into box pointers, and then we say create n boxes, generate n boxes using this lambda function, which will just call this function here, spawn. Simple enough, I think. But yeah, I just forgot to mention that when I was talking about the base code. Anyways, so color traits was moved. Box.cpp, what changed here? All right, that's just color traits was moved out of there. No big change. So the other big changes are in game.cpp. So what we do here, instead of creating a whole listener class, we just create a static pattern matching listener, and then we add some cases. So case, these template parameters are the two things that we are going to be handling, the combination. We want to handle a case of red colliding with white. We pass it a lambda function that takes a box pointer to, or reference to the red one into the white one, and we give the actual behavior, which is a mark to death. So we want to mark the red one for death if red collides with white, and we want to mark the blue one for death if green collides with blue. And there you go. This is how you set up your cases. Very simple, very easy to read. And then here at the bottom, you set the contact listener to our listener object. And the rest of it is completely the same. You're still removing the dying boxes, and that's all there is to it. So yeah, the trick to this, I guess the biggest trick to the pattern matching, is figuring out that you need to do a pair of pointers to type info. If you can figure that out, the rest of it just kind of follows naturally. But now what I've seen some people doing, or at least one person, was what they did was instead of switching, or instead of mapping on a pair of the unique type info, they were mapping on a string, on a single string that was a concatenation of the names of the two types. Or no, they weren't even switching on that. What they were switching on was they would accumulate the ASCII values of all the characters in a string, which was a concatenation of the names of the two types, the dynamic type names. So it would be like class yellow trait, class green trait, concatenated together, and then they would run over that string, add up all the ASCII values, and that would give them an integer value that they would use in their map. But this is a problem because you can have different ASCII strings that actually add up to the same sum of values, right? It's not even that difficult. If you have a lot of types in your system, the chance of you having a collision like that is not particularly low. So it's not a good solution. Your unordered map for a combination, for a pair of things, the value, not the value, the key should be a pair of things, because that's what you're actually mapping, a pair of type infos, or even a pair of class names. And so if you went the class name route, then your pair wouldn't be pointers to type info. It would be a pair of strings. The equal to would be the same. Well, it would be similar to this, right? It would just be comparing the two strings to each other. Left-hand side equals right-hand side. And the hash would be, it could be anything really, but you could hash both strings and combine the hashes, or you could concatenate the strings and then take the hash of that string. Doesn't really matter. So you could do this with something else. You could do it with the names of the types, or you could do it with the actual colors themselves as ints, but you can't fold them together and put a single value as the key. You have to maintain them as separate values and then compare them with the equal to and hash them together with the hash. That's the important part of making a pattern matcher like this. But anyways, that's how the pattern matching works. So the next thing I did here is I suggested you add different effects than just destruction. So the one I added here was tag, where two collide, one will get the color of the other one. And the way I implemented that was I added a little member function to box called assume color trait, and you pass it a reference to a box, and it will get the color trait of that box by cloning its color trait and assigning it. So that will destroy the existing color trait, and it will now point to color trait, which is the same as the one of box B. And then in game.cpp, it's very simple. You just add another case here. Mr. Lister case, we'll go yellow and blue, and here we have blue assume the color trait of yellow. And that's all there is to it, to add a different little effect to the system. All right, the next behavior that I added was the splitting. So I wanted to be able to have an effect where you can split a box into 4 parts. So the way I did that, start off with, we'll look at that in a second. So in box.h, added another function called split. And it takes a world, a pointer to the world, and it will split the box, and it will return a vector of pointers to the children boxes. So this is going to destroy the current box and give you a vector of pointers to the new boxes that were created. And it will create them, it will create the boxes, the entities in our system, and it will also create the entities in the world. So the way that works is, so we create a vector that's going to hold the new boxes. We get the position of the current box, the angle, the velocity, the angular velocity. We want to maintain the momentum before and after the split. So that means that all of the boxes, the children have to have the same velocity and the same angular velocity after the split that they had before it. Now the tricky part here is, let's say you've got a box in the world and you want to split it. So after the split, it should look something, let me just draw up boxes. So it should look something like the blue one here, split into 4. Now, if we do the naive approach, would be, okay, I'm splitting the box, so I will create 4 boxes that are half the width and half the height, and I'll just spawn them at the same place as the current box. But that's going to give you 4 boxes that are stacked up here. That's no good. We want them in their corresponding places as they were before they split off from the main box. So in order to do that, you do have to do a little bit of rotational calculation. So if this is the center of our box, an unrotated box would have its the centers of its parts at 1/4 the width, 1/4 the height here, 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 and here. So you'd move away from the center by 1/4 of the width and 1/4 of the height in positive and negative directions. All those permutations will give you the centers of your new boxes, like this. Now, once you have that, you've got to rotate these points by the current rotation. That doesn't look right. Control Z, get rid of that. By the current rotation of the box. And that will put them in their actual positions. And then when you create them with the angles of the current box, and they will now be like this. So, how do we do this? Well, first we get the base. We get a base vector for rotation. And that base vector, well, this is a little different than what I mentioned to you. But basically, we put our box, our starting position here. We started off relative to the origin, relative to 0, 0. And we give it, again, 1/4 the width and 1/4 the height. We put it right here. And what we're going to do is to generate these 4 guys, we're going to rotate it by pi over 2, or by pi, or by 3 pi over 2. And that will generate the other base positions. And then once we get those, we want to rotate them by a further whatever the rotation angle of our box is. And that will give us the final position. And now, because this is relative to the origin, we have to add to that this vector here, the vector to the actual position of the box, and that will translate them to the real position on the screen. So that's the general idea. So this is the base, the singular base vector, 0.5 times size. Size is the half width and half height of the box. So this is 0.5 times half, which is 1/4 of the width. And we give this, so we start them off automatically with the rotation of the box. And the way we do that, the way we rotate the base vector, is we multiply it by a rotation vector matrix. So we can create a rotation matrix, multiply our vector by that, and that will give us the rotated vector. And then for each of the 4 boxes, we clone the color trait. We give it the world that it needs to create itself. The vector here is the base times the rotation times I times pi over 2. And this is how we generate the 4 different boxes, because this is I is going to increase by 1 for every box. This will generate the positions of the 4 boxes rotated around from the base vector. And then we add to that the position of the parent box. And that gives us the positions of the boxes in the world, the children boxes, as they should be. And then we get the size, which is the width and the height, or the half width and the half height of the children are half that of the parent. Angle is the same as the parent. Velocity is the same as the parent. Angular velocity is the same as the parent. And there you go. We generate the 4 children boxes. Then we mark the parent for death, and we return those boxes. Then in game.cpp, I haven't attached this to an event yet. So what I'm going to do, just to test, is do some key press stuff. If I press the space key, split the first child that is in my vector of boxes. That will give us a vector of children, and then insert those into the vector of box pointers. Or move it in there, actually. There you go. And then you're going to remove, again, the dying ones. That will remove those that have died due to collision, and that will remove those that have died due to splitting. And there you go, you got it. So if I set my solution, if I set my checked out branch to solution 4, let's put in a release. If I build that, hopefully it builds. Otherwise, something has gone very wrong. So we can see here that the destruction is going on, and if I press space, we can split. There you go. Beautiful. Lovely splitting action there. So there is the splitting mechanic all handled up with proper conservation of momentum and nice seamless split. If you spawn them all in the same place, they're not going to split nicely like this. Like, take a look. Bam! You see they just kind of fall apart like that. Beautiful. But if you spawn them all in the same place, they're all jumbled up together, and then they kind of have to push each other out of the way. It's not as realistic. But anyways, there you go. Now, the next thing to do is to bring that splitting into the event system. Now, the problem with bringing it into the event system is that the splitting actually destroys a box. It tries to introduce boxes into the world, and it destroys a box, which is not something that you want to be doing in the middle of your, let me see here, action split. That's not something you want to be doing right in the middle of your handling or in your stepping of your simulation. So there are a number of ways we can handle this. We could add another flag for splitting, and then here we'd add a loop that checks the flag for splitting and, does the split if anything is meant to split. But that, you can see right now that will start to cause a problem. How many effects do we want to support? And how many of those effects are going to have impacts on the actual Box 2D world? Do we have to add a separate flag for every one of those effects? You see, that doesn't scale very well. So what I'm going to do, instead of that, is I'm going to implement an action system. So an action is going to be a basic class. It only has one pure virtual function, the do function. Now do will take a reference to the container of boxes, and it will take a reference to the Box 2D world. And we can inherit from action and create specific actions that we want to have happen. Like, for example, the split action. Now, the split action, when we construct it, it will take a reference to the target box that is to be split. And when we call do, it will implement the split. The tag action will take a color trait, and it will also take a pointer to the target, the box target. So we'll take it as a reference. We'll store it as a pointer to the target, and we'll also take the trait. And when we call do, it will apply the trait to the target. So by having this action class, we can separate the basically the creation of an action or an effect with its actual execution. So we can create actions in our collision handler, and we can execute the actions later on after the simulation has completed. That's the idea. So in box.h, not in box.h, in game.h, we're going to add a vector of unique pointers to actions. These are our actions, our polymorphic actions. What did I add to box.h? Because I'm not sure here. Oh, assume color trait. Now, instead of taking a box, it takes the actual color trait and it just moves that in. Okay, small change. Big change in game.cpp now. Because now what we're going to do, I removed this key press stuff, by the way. Now what we're doing is after we step the world, we're going to run through the array of pointers to actions, and we're going to call do on each of them. We're going to give it the world. We're going to give it the vector of boxes. We're going to give it the world, and it is going to execute all the actions. And then when we're done that, we're going to clear the actions, and then we're going to call erase to remove all the things that actually died. And here, what we do is now when we have an action, like for example, what do we got here? Tag. I think this is a tag action. So when yellow touches blue, we're going to push an action back into our vector. We're going to make a tag. We're going to pass it the target, which is the yellow one, and we're going to pass it the color that it should be tagged with, which is the color of the blue, the B box. And there you go. And for destruction here, no, this is for splitting. Again, we only want to split. We want to split the one that is larger, and we only want to split if it's larger than a certain threshold. We don't want to keep splitting infinitely because that'll crash our program. So we want to split until they are less than or equal to 0.2. And then we're going to split the one that is larger. And we call split. We create the split action. We push that into the action pointers. And that's going to get called down here. And when it gets called, it's going to add some to the vector of box pointers. And it's also going to destroy one, or going to set one's destruction flag. And then in here, it's actually going to be removed. And there you go, you got your action system. And this is scalable no matter how many different kinds of actions you add to your system. You just inherit from action, and you create it in here, and then it will get processed in here polymorphically. Now you might be wondering why I didn't make destruction an action. And that's a problem because destruction actually removes something from the vector, right? But what if you had other actions that were targeting that box and you remove it from the vector? Those actions are now going to be targeting something that doesn't exist anymore, and they're going to crash. So destruction is special. You need a flag for destruction because you only want to destroy after you've processed all of your actions. But for everything else, you can process it as an action inside this loop here. So you see here for the destruction, we still only call mark for death. You could make a system that is all actions. It does not have any flags, but that would require something called shared pointer. It would be quite a bit more complicated. I'm not sure if it's worth it. I think the nice trade-off here is use a flag for destruction, and for everything else, use an action. And if there are any actions that have a side effect of destruction, they just set the flag. Destruction is only handled by the destruction flag here. But there you go. There is your action system that you can use to add any number of collision effects and to stack them up. And all you do is when you want to trigger an effect inside of this case here, you just push an effect or an action into the vector. Beautiful. It's a nice little pattern here. I'm sure this is fairly similar to something in the Gang of Four, maybe the command pattern, I'm not sure. But it's a pretty common design pattern. And that, my friends, is basically all the stuff implemented that I requested that you implement. Now, there's one little thing I just want to add here, a little bit of spice. Definitely not required, but maybe a little interesting. So you might note that for our pattern matcher here, we're templating it on T and U, and those template parameters control what patterns you're going to be setting for the case. But you might have noticed that they're not restricted in any way. You could pass in anything you want. You could pass in int and a pub, and it would create a pattern matching case for those, even though that doesn't make any sense because your listener is only going to be listening for color traits. So it's dumb, and it's not a big deal here, but in a situation where you've got a lot more classes that could be candidates, and maybe some of them have very similar spelling with a completely unrelated class, by a simple misspell, you could create a listener that's listening for something that you don't want to listen for, and you could fail to create the listener for the actual thing you wanted to listen for, just because of a small typo. Now, to prevent, you can do a little bit of something to prevent that situation. And what you do is you include type traits. And we're getting a little bit into something called template metaprogramming now. Because what you can do is you can actually, at compile time, you can check to see whether that T or U is something that you actually want to be passed into this function, or that you want to template this function on. So what you do is you call std is base of, and you can check to see if T, or if box color trait is a base of T, if T is derived from color trait. And you just do value here, and that'll return a bool. Now we'll evaluate to a bool at compile time. And static assert is an assertion that is checked at compile time. So you can issue a compiler error if someone passes in a dumb type parameter for T or U. And you can give it a nice little message here, like template param type T must be derived from box color trait. So you can do those here, and you can kind of do a little bit of smart checking and eliminate some dumb errors. You could actually also in here, and I can't do this because I'm working with Visual Studio 2015, but with Visual Studio 2017, you have access to a function std is invocable, or something like that. I forget the name. And you can actually also test the type of this function, and you can make sure that it's a function that returns void and takes reference to boxes. So you can, what's the word I'm looking for? You can reject functions that don't fit your specifically required signature. And I mean, those will be rejected at compile time eventually because they won't mesh with the unordered map. But if you put static assert up here, you'll get a much nicer error message with much fewer bullshits in your template error messages. But anyways, that's we can't do that right now because I'm working with 2015, but it's something to be aware of. So yeah, you can use this type trait stuff at compile time to check your template parameters and maybe to give some nice errors for them. There's other things that can be done as well, but that's more deeper into the realm of template metaprogramming. Not going to get into that today, but just a little bit of spice at the end here to show you something that you could do to make your functions here a little tighter, a little more type safe. But yeah, that's the solution to the homework. I tried to make it as detailed as possible, as you can tell by the length of this video, but I'm sure there's still things that I've glossed over. And if there's anything that you're wondering about, you can leave a comment here on the video. You can message me in the Discord. You can leave make a post on the forum, and myself or someone else will give you some insight. But until then, I hope you enjoyed this little more in-depth challenge for the end of intermediate, and I will see you soon with some more C++. We're going to be starting advanced, and it's going to be a good time. See you soon.